and go through. So we'll real quickly roll the die, talk about homework turn in, and then we'll pick up where we left off last week or last class, talking about quantum mechanics, electron behavior, which today for us will be talking about clouds, which we'll use balloons. And then we're going to work through, oh, excuse me, coffee burp. Woo. And then we're going to start working through the mighty packet of electron arrangements. So to start off with the homework, I sent out a little message yesterday that gave a correlation between the homework problem and the practice problem. Did you guys see that, and was it helpful, or do you need me to send it again?
I saw it.
Can you send it one more time, please?
Yeah. Okay. So I will send that again, but it does literally tell you. So when you're doing question number 4 on the homework, go look at the practice at question number 4. They're set up the same way, that type of thing. So that should help you with any of the calculations. All right. Rolling of the die. Rolling of the die. I'm just going to throw it straight up because I've got a bunch of stuff in the back here. I'm checking 5. So this had, how many questions are on this one?
8.
8. There we go. Okay. I'm checking number 1. That seems easy. I'm checking number 6. Four. 2. So 1, 2, 4, 6, and there's not a number 9. I already rolled a number 1. I already rolled a number 2. 8. So 1, 2, 4, 6, 8 is what the grade will be on. 1, 2, 4, 6, 8. And then there's the Google form. That form link is in the plan. That makes it much, much easier for me to grade. And then also send me the scans. So a couple of people have already turned their problems in. I saw last night. But again, this is counting for term 4. Because it normally is several lag days to be able to get everything in and graded. And tomorrow's the last day of the term, so guess what? This will count for term 4. So I'll get them graded over the weekend, and then it'll end up getting counted for term 4. I still do not have any information about term 4 and grades and all that sort of stuff. You know, up till now, everything that you've done, you can't be penalized for not doing it. I suspect that will not hold true going forward, because term 3 we had grades. We don't have any grades for term 4, so you have to turn stuff in to get grades. So but that's what I have no idea, so I can't answer any questions about that. But this assignment counts for term 4. That's what I know. Okay, so let's return to quantum mechanics. Because I think quantum mechanics is fun, because it is. It's magic. We're talking about magic. Really, we're talking about addresses. It's like you're writing a letter to an electron, and you need to tell it where to go. So essentially what we're dealing with is mathematical, these wave equations that Schrodinger came up with, these giant page-long things that had 4 variables to them. These things generate statistical models that are called probability distributions, but we call them clouds because that's kind of like the scattershot shape of them. This is like all some advanced level statistics and whatever. Fine, cool. What does all that mean? Well, first off, we have energy levels. So Bohr had the rings. We don't really consider them rings anymore, but we still consider them to be energy levels. And our energy levels are represented by the letter N, which you've probably seen on stuff we've been doing before, like on the Bohr models, you've said N equals. That's referring to the energy level. And our energy levels are just numbers, 1, 2, 3, 4, right? 5, 6, et cetera, et cetera. And you should know that the higher the number, the farther away from the nucleus that energy level is, which means it's bigger, right? So a number 1 is going to be small compared to a number 2, 3, 4, et cetera, et cetera. So that's all common sense and basically sounds exactly like Bohr. It's all the other stuff I'm going to say that's like a little on the different side. Okay. So in addition to energy levels, you have sublevels. Sublevels would indicate a part of an energy level. And the sublevels have letters, S and P and D and F. And technically they're represented by a lowercase l, but SPDF is what we need to know, SPDF. And the S, the P, the D, and the F corresponds to the specific shape of the distribution cloud. And then the other thing that you kind of have to know is not all the energy levels have all of these S, Ps, Ds, and Fs. But I want to show you these. This is where balloons come into play, what these things look like. So I'm going to stop sharing really fast and have it freeze on me because I can do that. Okay. So the first one is S. And S has a very nice little shape we would typically refer to as a sphere, right? This is a sphere shape. So this would be the 1S, right? 1 being energy level is kind of smaller. S is the shape. But I could have a 2S. So it's the same shape, but it's much larger. That's where we mean that the 1s, the 2s, the 3s refers to the size, and the letter refers to the shape. So my S is my simplest shape. It's my simplest distribution. It is what you imagine a Bohr model would be, right? Like a circle. And we refer to it as a sphere. Basic. Okay. The P. Well, the P gets a little bit more complicated. So P itself is an individual thing that looks like what we refer to as a dumbbell. Don't ask, I mean, it's not, I'm not getting big if I'm lifting this as a dumbbell, but it's kind of got this shape to it here. And the thing about P is there's actually 3 parts to the P cloud, right? And I've actually labeled them as PX, PY, and PZ because they're in 3 dimensions. So these things actually, you can hire me out for parties. All right, so they actually make something that looks like this. It looks kind of like a flower. And this is the actual shape of the P cloud, right? So where there's like literally nothing in the middle, but then it's all collected on these outside edges here. So that's what a P cloud looks like. And then D starts going into these like clovers. And D, you would have tons of these things. And then I'm not even going to get into what F looks like because I can't make F out of balloon animals because I'm not that skilled. But I'm gonna refer back to these in a second. So let me share my screen again. Hi, Josh. I'm glad you're not dead. Thanks for joining us. Okay. So we've got SPDF. Next, each of those sublevels have orbitals, parts, bits to them. So this is going to make sense again when you look at the parts. So S has 1 part, P has 3 parts, D has 5, F has 7. So there is a pattern here, right? It's 1, 3, 5, 7. They're going up in odd numbers. And then it's really easy to see again. This is S's 1 part, right? It's only 1 balloon. Like, that's easy to see. And there's, at any one point in time, 2 electrons in or on this space. So what electrons are doing is they are simultaneously appearing and disappearing on basically what the surface of this balloon would be. That's what's happening. So an S can have 2 electrons occupying this sphere space. P, however, had 3 parts, it said, right? 1, 3, 5, 7. So 3 parts. So I color coded them so you can see that there's the purple set, there is the orange set, and there is the red set. So I've got 3 parts of my balloons. So 3 parts of my sublevel. So those are my 3 orbitals. And each one of these can hold 2 electrons. And it should kind of make sense that I can have 1 electron appearing and disappearing up here, 1 electron disappearing and appearing here, 1 appearing and disappearing here, and here, and here, and here, for a total of 6 electrons. So the P has spaces for 6 electrons to be and not be around each other. So they're kind of spread out. So S is 2, basic, P is 6, and then once you start getting into the bigger shapes, so this D, there are 5 of these, and each one of these holds 2 electrons, and you can imagine these are going to be bigger, they've got more energy, so they need more space. So you can imagine that there's 1 electron that is appearing and disappearing back and forth in this shape, and 1 that is appearing and disappearing back and forth in this shape. So you get 2 electrons in this X pattern. But if you had 5 of these and each X is 2, that means D holds a total of 10 electrons. So 2, 6, a bunch more of these gives you 10. So if F has 7 parts, how many electrons do we think F can hold?
Electrons?
14. Okay, so we've got S can hold a total of 2, P can hold a total of 6, D can hold a total of 10, and F can hold a total of 14. So we've got some pattern going here, the 1, 3, 5, 7, the 2, 6, 10, 14. Those numbers we're going to be working with a lot, and you are going to have to kind of know those numbers. So those are the orbitals. So that's all kind of easier to see. So you've got the sublevel, each sublevel, or you've got energy level, each energy level's got some sublevels, the sublevels got parts, the parts are where the electrons are. Then we said that there were 4 variables for those stupid wave equations. I've only listed 3, energy level, sublevel, orbital. So what is the last one? Well, it's called electron spin. And the electron spin is just kind of a random thing. It's not actually that an electron is spinning. It's more of like an accounting measure. So we say that 2 electrons can't occupy the same space in a sublevel, right? Or in an orbital. They can't be in the same space. So to technically designate that they're in opposite spaces, we give them opposite spins. So think like an up and a down, right? Or positive and a negative, right? They're opposite. So that way they're not trying to occupy the same space. And that's just more of a mathematical designation. But One thing we do not have to do anymore is actually go through and assign all of these what are called quantum numbers. We don't have to do that. We just kind of have to like know what to do with that information. So that's an outline of what all these pieces are. And now we're going to go into, so what do you actually do with all that stuff? So this can be a little confusing, but that's why I actually think that the section 5.4 doesn't give you enough information to understand what they're trying to give you. So that's why I've created these other two packets. This first one, which I did send the file of in case you lost yours, is there. I sent it through Remind, but that's the guy you need to be looking for. So it's really not actually that confusing because there are patterns. There's so many patterns, and there's several shorthands and shortcuts to all of this. So it should be a little bit more apparent as we go through it, and we will spend several class periods going through this. So I need you to get this thing out. And if you do not have this thing and you did not print out the thing that I gave or that I sent out yesterday, if you couldn't find your thing, then you're just going to have to watch what we do. And then when you find yours or print out that file or whatever, then you're going to have to rewatch this because you're not going to be able to keep up with what I'm doing on just scratch notebook paper because it's a lot. Okay, so I'm going to switch over to my iPad. Come on, there we go. Okay, so this whole thing, this entire packet is teaching you how to write the address for an electron two different ways. We have to know where the electrons are inside an atom so that we know what kind of reactions, what kind of bonds, what kind of chemistry can happen, because all of chemistry is based on the electrons. So you gotta know where they are, because otherwise you don't know what it's gonna do. So we have different levels of complexity in our address. We have what is called an electron configuration, and I will show you that this thing here, that is what we refer to as an electron configuration. I feel like configuration is just another way to say the word arrangement. So that's an electron configuration. That's a very condensed shorthand. You can write it on one line. That's our primary goal, is being able to write those things. This whole thing, which is a lot, it takes a lot of space, but there's a lot of information in it, is called an orbital diagram. So if you were trying to send a letter to somebody's house, you would write an address like an electron configuration. It tells you the state, the city, the zip code, the street number of the house, that sort of thing. If you were in Harry Potter world and you were trying to send an owl to Harry underneath the stairs, you would do an orbital diagram because it's got a lot more specific information about location. Most of us do not live in Harry Potter world and do not need to send owls, so we don't need orbital diagrams most of the time. Most of the time, an electron configuration for an address is going to work perfectly appropriately for us. We don't need more than that. So there we go. Okay, so all of this information here, and then we've got these questions down below. Come on. Okay, so let's start off by matching these various different parts. So looking at all of this diagram, what seems to represent a single electron in one of these things? The box, the arrow, the pair of arrows, the set of boxes, or
An arrow.
a single arrow, right? Okay, so a single arrow is an electron. So a pair of electrons with opposite spins.
2 arrows.
The 2 arrows. Yes, this is not that complicated. Okay, an atomic orbital, which is a region of space where an electron is likely to be found. The single box, the set of boxes, or the number letter things?
Single box.
Single box. Bam, bam, bam. So that means if you have a set of boxes, you have a sublevel. And the electron is that letters and exponents and all that sort of stuff. So this is where I mean, like, a sublevel is made of orbitals that hold the electrons, right? So it's like a full sublevel is made of individual orbitals that hold the electrons that can have opposite spin. So that's why it's like it dials down. So there's a lot more information in this thing than there is in the electron configuration. But if we're looking at all of this, do you see how the number, where are you getting the number of arrows that should be in a diagram if you're looking at an element?
From the charge.
Not the charge,
The electron configuration.
but how do I know how many electrons I need to put in my electron configuration?
Don't you take the atomic number and subtract it from the charge?
Right, we are eventually next week going to talk about charges, but right now we're talking about plain Jane, neutral elements.
Oh.
So it is just their atomic number is all it is we're going to be dealing with. So with that being said, it says consider oxygen up above. So this guy, I'm going to rewrite it. Oh, they already wrote it. So how many electrons are in this diagram? This one. Oops. How many electrons are in there?
2.
1, 2,
Oh wait.
3, 4.
You talking about in one box or
Five.
all?
In the whole thing.
Oh.
So in the whole thing, there are 8. Okay, so how many electrons are present in the diagram? So there are a total of 8. And it says, based on its position on the periodic table, explain how you know that your answer is the correct number for oxygen. If you look at a periodic table, what does it tell you for oxygen?
It's 16.
Its atomic number.
Or its atomic number is 16.
Its atomic number is 8, right? So we've spent all year focusing on the atomic masses because that's what we use for molar mass. This is the one time period where we're actually going to care about the atomic numbers because that's where we get the number of electrons. Okay, so let's break down the electron configuration a little bit first. So it says, using this, the 1s2, 2s2, 2p4, underline the energy levels. So what should I underline in this 1s2, 2s2, 2p4? What represents energy level?
The numbers?
The big numbers, yes. 1 and the 2. So then what represents the sublevels? What are we going to circle?
The letters.
The letters. S, S, and P. So that means by default, these must be the number of electrons, these exponents. And if I add up those exponents, what number do I get?
8.
8, which is what I should expect for oxygen. So in an electron configuration, it tells us an energy level, a sublevel, how many electrons are in the sublevel. Then the next energy level, sublevel, how many electrons are in that sublevel. Energy level, sublevel, how many electrons are in that sublevel. Add up all of those electrons and you get the atomic number. So the way this thing reads, while those are exponents, we do not say them as, say, squares. So that would read as 1s2, 2s2, 2p4. That's what an electron configuration sounds like. And you can imagine that when you're saying one of these that's really long, we all sound like we're doing some weird chemistry chant, 1s2, 2s2, 2p6, like on and on and on, because the pattern stays the same. So, all right, so we're going to move on to the next page, and it's going to kind of back and forth us a little bit. Okay, so it says the 2s and 2p sublevels are very close in energy, as are the 3s and the 3p. How does the orbital diagram for sodium confirm that 3s is lower in energy than 3p? So it said for sodium. So if I look at this thing, how do I know that this is lower in energy than this? You should focus
Because it's
on,
actually lower.
all right, so there's two ways. One, it's physically lower in the diagram. Okay, so it is one of the reasons why the diagram is done that way. So it's physically lower in the diagram. And then also, where did the electron go? Where did the electron end up occupying?
It ended up occupying the S.
It ended up occupying the S. So you have to remember, if we're talking about like ground states and excited states, right? We said electrons want to be in their ground state. They want to occupy the lowest energy possible. So wherever an electron is must be the lowest energy space that was available. So if it hung out in 3s, that must mean that 3s is a lower energy position than 3p. Okay. So the electron, and I'm just going to do an E minus for the electron. The electron occupied the lower energy spot first. Okay, so like I said, electrons want to be in that low energy ground state possible. So when they fill up inside all those energy levels and sublevels and orbitals and all this stuff, they are going to fall into the lowest energy space that they can find. This is a German word called the Aufbau principle, and it basically means filling up. And I kind of like, and everybody's home now, right? If you haven't ever watched it before, go watch Price is Right. See if they're playing the Plinko game. In the Plinko game, you drop the things at the top and then they hit the pegboards and they fall all the way down. This to me looks like a Plinko electron funnel, right? You dump electrons up here at the top and they're going to fall down until they get a little spot for themselves. And they will keep falling. You can't have something that hangs out up here if there's a space down here. Like they have to keep falling down until there's 2 electrons in a box. That's what they do. So based on this, based on where a single electron is placed, the lowest potential energy electron in an atom is found in which of these energy level sublevel combos? 1s, 2s, or 3s?
1s.
1s, always. Every single electron configuration or orbital diagram always starts with 1s. And then you're only going to go up to a p after which of those things? You get a half-filled s, a completely filled s, or an empty s. You can only go up to p when you see what in your s's.
S.
Does it have to be totally full, half full, or empty?
Totally full.
Totally full. All right. So it has to be completely filled. You have to fill up before you move on. So it says electrons can begin to occupy energy levels with the higher number only after which of these things? Half the orbitals below it are filled, all of the orbitals are filled, or at least one of the orbitals are filled. So half, one, or all?
All.
All. All right, so again, you got to fill up all of the orbitals. You can't leave any gaps in your electron configurations. You got to fill up as you go along. So that makes sense. Then we have this other thing coming from a German man, Wolfgang Pauli. I think Wolfgang is an excellent name for a child. So the Pauli exclusion principle says that if you're going to put electrons into the same orbital, into the same box, they must have what? Opposite spins or the same spin?
Opposite.
They've got to be opposite, right? You look, all of these arrows, one up is one, you have one up and one down. We always say that they have opposite spins. That's that whole last thing. You know, spin is not a real thing. Electrons are not actually arrows. They do not actually go in opposite directions because they do not actually move. Remember, the magical motherfuckers, they appear and disappear. They don't actually move. So it's a little bit different there. And then the last rule for these things is what I actually refer to as the empty bus seat rule, because we are people who live in a metropolitan area and take public transportation, and whether you were explicitly taught this or just kind of picked up on the rules of society of how you operate on a bus, you know what to do in various different situations with empty bus seats. If you are getting on a bus and there is a pair of seats that are empty and there is a single seat that is next to another person, societal rules say you do not go sit next to some random stranger if there's two empty seats. You go sit in the two empty seats. If there's a pair of empty seats, you go sit in the pair of empty seats. Electrons do the same thing. You only sit in a single seat that is next to a stranger if there's no other options. That's it. And electrons will do the same thing. So electrons are only going to pair up in seats when there is a single electron in everybody. And if you look at that, let's see who's got that. Okay, so if we look at these two, all right, so this is what I'm talking about. Look at that. Everybody took their own seat because they don't know each other. So they sat by themselves, because you're not going to do the socially awkward thing and go sit down next to a stranger if there's a bunch of empty seats on the bus, right? That freaks people out. So electrons don't do that either. They understand societal normal rules. So everybody take their own seat first. And then once everybody has their own seat, then you can start, if you keep adding electrons, then you start pairing up. And when you pair up, you are going to have to sit in the opposite direction. So everything is going to, in the same sublevels, all going to have the same spin, so that then you can pack them in this way. So it always ends up looking like this. Electron number 1, electron number 2, electron number 3, and then you'd fit back in and say electron number 4, electron number 5, and electron number 6. So up, 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 and then down, down, down. That's kind of the way it ends up working. That's how you pack electrons in. So it's like if you're trying to pack a box or something, you have to do it with some sort of order, otherwise it doesn't work. So let's look at this bottom set of diagrams. Only one of these looks right, and the other two look wrong. So this is supposed to be for nitrogen. So the very first thing you should think about is, if I were nitrogen, how many arrows or electrons should I have?
6.
7.
7.
7.
All right. Should be 7 because that's its atomic number. Okay. And you should always start at the bottom. So you're always going to fill the first box with its 2 before you move up, et cetera, et cetera. So looking at this first one, there are multiple things wrong with this first one. Name something.
They didn't fill up before it moved on to the
Right.
energy levels.
That guy should not be there because I've got an empty space here that should be filled before this. And I've got an empty space here that should be filled before this. So this is what we would say it violates the Aufbau rule, right? That's the filling up. You have to fill up in order. This did not fill up. What is the other real basic thing this person did?
It doesn't have enough electrons.
Doesn't have enough electrons. Okay. So what about the second one? Does the second one look like it is correct, or does it look like there is something funky going on?
It looks correct.
It is correct. So all 3 of these arrows facing down, well, that like violates every part of my soul and makes me like cringe because I want to draw them up. It is okay that they are written down because they are all down. So they either have to be all down or all up. Yeah, that bothers me because I would write them up. But this is technically correct. I have filled in every box as I have moved up my energy levels, and then once I have gone into these open spaces, I have followed the empty bus seat rule, putting 1 electron in a box, and they're all facing the correct way. So that one is correct. And what is wrong with the last one then?
It didn't fill up every box until they click an opposite arrow.
Right. So this guy violates, it's called HUND, but I'm going to say the empty bus seat rule. Because this electron should not be there. It should be in this space over here, right? You can't pair in, and you've left an empty seat. So that doesn't work. All right, so we have finished half of this packet. I don't want to get into the next sets of diagrams and practice until we get there. But at least with this bit of information, if you haven't read section 5.4 yet, with this bit of information, section 5.4 is going to make a little bit more sense to you. But I can just kind of tell you these 2 diagrams on the next page, these give you the order that you fill so that you know that it's 1s, 2s, 2p, and then I'll tell you it's 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4s. You are following this red arrow is what's telling you the order. So like this guy here on the right, this is what I refer to as the master orbital diagram. So you can figure out anything based on this. That worksheet at the front was only showing you this little set, but the pattern continues up above. We don't write orbital diagrams for large elements because having to draw out this giant diagram there on the right would be a huge pain in the butt. So we don't do that. That's why we write the electron configurations. And this red arrow shows you the order of these electron configurations, right? It tells you what the order goes. So you do start with energy level 1, sublevel S, and then the red arrow says then you follow 2 and then S, and then the arrow says you follow 2 and then P, because it's like chutes and ladders, right? You go down here and you start up at the next arrow, right? 2P, 3S, and then the arrow says go back up, all right. 3P, and then it gets weird because from 3P you jump to 4S, but there's all these D's and F's and we just kind of skipped them because, well, we're following the order of ground state energy. And you know what? 4s is lower in energy than 3d, so it goes first. So then it would go to 3d, and I follow the arrow 4p, and I follow the arrow 5s, back up, and it says then 4d, 5p, 6s, et cetera, et cetera, et cetera. So we'll pick up next class with that guy, and we'll go through these practice problems, and then we'll jump into the next packet, which is going to teach you, once you kind of learn how to do an electron configuration, I will teach you how to condense it and shorten it into what's called a core notation. And that's what your video is on for Monday. It's on how to start condensing electron configurations, so that it all kind of goes together. All right, so video 31 is due Monday, so that counts for term 4. We're going to finish up this packet, and then you need to find the next packet, which should have been right behind it, the advanced electron arrangement topics. I will also send that out as a file at some point over the weekend, so that you have that in case you lost it. Then I have found some ways for you to practice this that I will be sending out, so that you can do things that are not just like homework, but you can just practice it, just to practice it. And then we're going to start using the Google Classroom next week. So I haven't looked in a couple of days, but there was only like maybe 10 people who were signed up for it, and there should be like 40. So the link is on this week's plan. It was also in the weekend, the email I sent out on Sunday. I'll send out the link again. This is just to streamline how you're receiving information. So I will still email and make these weekly plans or whatever, but this way I'm trying to help you guys out so that everybody is receiving information in one location instead of multiple locations, just to make your life maybe a little easier. I don't know. Yeah, there you go. Don't have any office hours tomorrow because they got canceled because it's whatever they call it. I keep wanting to say it's reading day. It's not reading day. Records day. Woo! There we go. Records day. And that's it. So again, the homework questions that are to be graded are 1, 2, 4, 6, and 8. As soon as class is over, I will resend out the correlation of practice problems to homework problems, and that be it. So I'll stop recording, and if anybody has any questions, feel free to hang out and ask me your questions. Otherwise, have a lovely